Let's take a look at section 1.2. In this section, we're going to look at the order of operations. A lot of times this is known as PEMDAS. You may have learned this as please excuse my dear Aunt Sally. So way back in the day, that was kind of how I learned it. But it's the order of operations. It starts out with the parentheses. And all of these are in order from left to right. So that's very important for you to remember, is that everything is in order from left to right. So the parentheses can be seen as, sometimes you will see it with parentheses, brackets, and also absolute value. So that can sometimes be seen as parentheses. Also, like the numerator or the denominator of a fraction can also be considered to be seen kind of like a parentheses, and we'll see an example later on in our lesson where that is the case. Then you have exponent. This little thing right here is called an exponent character, and a lot of times you'll hear somebody call that a carrot top. And so this is called 8 squared, or 8 raised to the second power. What that means, that it is 8 times 8. This little character right here is for multiplication, which 8 times 8 is 64. So 8 squared is 64. So that's exponent. Multiplication and division go together. So a lot of times you'll hear me say parentheses, exponent, multiplication, division. So those two go together. So and it is in order from left to right. So in other words, if the division comes first, then you actually do the division first before the multiplication. And that's where a lot of students get tripped up in the order of operations. So multiplication, you'll see these different characters. You'll see a little star, an asterisk like this, an asterisk like this. You'll have an X, you'll have just a little dot. You'll have two numbers or letters written next to each other. That also indicates multiplication. And then division can be written as a slash. It can be written as a fraction bar, and then you have a division symbol. Then you have addition and subtraction. Most of us are familiar with the addition and subtraction, and these two go together as well, order from left to right. And just like the multiplication and division, addition and subtraction go together. So let's look at a couple of examples where we use the order of operations. So here's our first example. 10 plus 4 times 3. So I put our PEMDAS over here just to kind of remind us. So when we look at this, we don't have any parentheses, we don't have any exponents. So then we're going to look at multiplication, division, and you will see that we have multiplication. So we're going to do this multiplication first. So 4 times 3 is 12. And then we're going to bring down the 10 plus, and it becomes 10 plus 12. So 10 plus 12 is 22. And so that final answer is 22. So that's a pretty simple example for order of operations. Let's look at another example. So here is the same number written 3 different ways. So this is the same problem written 3 different ways. So now this first way, 520 plus 480 divided by 20, 520 plus 480 divided by 20, 520 plus 480 divided by 20. Now if you noticed when you heard me say them, it sounds like I am saying the exact same problem. It turns out that some of these problems are exactly the same, but not all of them. So let's take a look at how they're worked out. All right, so in this first problem, we're going to take a look at our order of operations. There are no parentheses, there are no exponents. Multiplication, division, we do have that. So here's multiplication, division, and it's a division, so we're going to go ahead and divide. 480 divided by 20 is 24. So then we're going to have 520 plus 24, and that becomes 544. Okay, so that's my final answer. Now let's look at the middle problem. In the middle problem, again, no parentheses, no exponent. We do have division here. So this is a division problem. Even though it looks like a fraction, that's 480 divided by 20. So I'm going to do that, and it's the same, 24. So then we have 520 plus 24, which again is 544. So it turns out that these first two problems are exactly the same. This is just two different ways to write the exact same thing, 480 slash 20 and 480 over 20. So it's just two different ways to write the exact same thing. Now, you would be tempted to think that this is exactly the same thing, 520 plus 480 over 20. However, it is not. And the reason is because what you have right here in the numerator, this is a big fraction, and in this numerator, it works out that everything in that numerator is understood to be together like there is an understood set of parentheses. So it's almost like they're glued together. You have to keep them together. And so even though you didn't see the parentheses there, they're understood to be there. So everything in that numerator is together. So we're actually going to have to do that first. So when we do that, we're going to do 520 plus 480, and that is 1,000. Then we're going to say 1,000 divided by 20. Now 1,000 divided by 20 is 50. So the answer to that problem is actually 50. So that is a huge difference. And so that's where the order of operations works very differently. Even though you had the same exact numbers and they looked very similar. So there you can see where the order of operations makes a big difference. Okay, let's take a look at another problem. Now, this is a big problem. So let's take a look at this problem and kind of dissect it first and see what we have. So when we look at PEMDAS, so we have 10 here kind of sitting off by itself. We have some brackets and parentheses. So here's a little set of parentheses and then a bracket and a bracket. So that means the bracket is kind of a bigger set of parentheses. So it's kind of like this is a bigger set right here. And then we have another kind of big set over here. So it's almost like we have three parts to this problem. We kind of have this little 10 guy over here. Then we have this section, and then we have this section. So I think I'm going to divide this up into three sections. So I'm put those lines in there just to kind of help me keep them divided into three parts. And that's just going to help me to not lose my place whenever I'm working through this. All right, so my first part is just that little 10 guy, and that's pretty easy. So what I'm going to do is I'm just going to drop him down. So 10, he's going to just go drop down, so he's ready, 10 plus, so no problem. All right, now I'm just going to concentrate on this middle section right here. So now I'm going to look at PEMDAS, and I'm going to look at order of operations here. So the first thing is I'm going to look for parentheses. Now, parentheses, I see this big set of parentheses, the brackets. Once you do that, you start all over again. So I'm going to go back and I start all over again. Inside of here, there's another set of parentheses. Okay, then once you get inside of there, you actually look and you start over again. Is there more? There was no more parentheses on the inside. So on the inside here, we ran out of parentheses. There was no exponent. So then it was multiplication division. So you were ready to do 15 divided by 3. So that's where the 3 came from. So we did 15 divided by 3. And so that's where this 3 came from. So then what we're going to do is we're going to do 3 and then times 7. And then this plus came from right here. All right. I'm going to go ahead and complete this. And that is going to be 21 plus. And I brought it down here to go with the 10. Okay, so that's the middle section completed. Now I'm going to do the same thing over here in this third section. So there's my big part of the brackets. I'm going to start over again with parentheses, and I have my little set of parentheses. Inside of that, I have 4 times 3. So I'm going to go ahead and do 4 times 3, and that's going to be 12. I'm going to drop down my divided by 6. And now I'm ready to do 12 divided by 6, which is 2. All right, so now I don't have anything else over here. There's no more add or subtract or anything, so I'm just bringing this 2 down. All right, so now my problem is 10 plus 21 plus 2. So now I'm ready to do 10 plus 21, which is 31, plus 2. And I add those together and I get 33. And that is my final answer. So it's kind of neat how you can take a really ugly problem like we started out with up here and whittle it away step by step and get a really pretty final answer of 33. All right, so that is order of operations. Now we're going to take a look at inductive reasoning. So inductive reasoning is a type of problem solving where you first observe patterns and then you predict answers for more complicated problems. So I was thinking about this, and I was thinking about in church work. When you have a growing church, some of you are going to be familiar with this. When does a growing church know that it is time to consider building a new sanctuary or worship center? So it's kind of been one of those things that has been made through observation. And you may have learned this already in seminary, that it has been said through observation over the years that they can predict that when a church reaches 80% capacity, so when your sanctuary that you're currently in reaches 80% capacity, that it is time for you to consider thinking about building a new sanctuary or worship center. And that has been based off of observations and that they're able to tell you that, okay, from past churches and experiences, that they know that if that growth continues to go, that you're going to run out of space. Okay, this is a type of inductive reasoning that they've been able to put all of these different things together and observe the patterns from previous churches to predict what's going to come. So that is a type of inductive reasoning. Now, on a mathematical scale, we look for number patterns. And so that's what we're going to look at now, is we're going to look for some different number patterns. So let's take a look at that. So we're going to look at one of your homework problems. And one of your homework problems, it kind of looks strange whenever you look at it. This is exactly how the problem is stated in your homework. And if you don't read your text, then you kind of look at this problem and you're just like, what in the world is it asking me to do? So it says this problem is modeled after example 1. Okay, just so you know, example 1 is found in your textbook. So you have to go through the text and you have to read the online text and then find example 1. And then it says find the requested pattern, enter the first 3 numbers of the pattern as a comma separated list. And then it just says 5 pattern. So it's just like, what in the world are they talking about? Okay, so I'm going to walk you through what the 5 pattern is. So they give you an example, and example 1 in the textbook is the 9 pattern. So it turns out a mathematician named Polya came up with this observation where he took these numbers and he realized that he came up with this really neat observation. So the 5 pattern would be that if you take the number, let's take, and we're going to do all of the multiplications of 5. So we're going to say 1 times 5 is equal to 5. Then we're going to say 2 times 5 is equal to 10. And then what we're going to do is we're going to take the digits of 10 and we're going to add those digits together. So 1, 0, and we're going to say 1 plus 0 is equal to 1. All right, there was only one digit in 5, so there's nothing for me to add to it, so it's just a 5. But this one would be 1 plus 0 is equal to 1. All right, now, then we're going to go 3 times 5. So 3 times 5 is 15. So then I'm going to say 1 plus 5. 1 plus 5 is 6. All right, so can you tell me what the next pattern would be? So it would be 4 times 5. So if it was 4 times 5, then what would it look like next? Okay, so 4 times 5 is 20, and 4 times 5 is 20, and then 2 plus 0 is 2. Okay, so now here is the actual pattern. The first numbers of the pattern would be 5, 1, 6, 2. Okay, so what you would do, it says enter the first 3 numbers of the pattern as a comma separated list. So the first 3 numbers are 5, 1, 6. And then that's what you would enter into WebAssign. So this would actually be your answer. Now, what he ended up finding was that whenever you enter this in, because I'm sure you're probably thinking, what is the pattern here? Because I'm not seeing the pattern. If you keep going, you end up getting all of the digits and then they just repeat. So you end up getting like all of the digits 0 to 9, and then they keep going, like they just repeat. And so anyway, it's a pattern. So if that fascinates you, you could try it and just keep doing it, or otherwise you can just take my word for it. So anyway, but this is the answer. So, but you'll have another question similar to this for your homework number 5. It may say the 7 pattern. And if it was the 7 pattern, you would say 1 times 7, 2 times 7, 3 times 7, and so on, or the 8 pattern or something like that. So, but that's what this is. Okay. All right, so let's look at another question. So this is inductive reasoning. It's where you are looking for patterns, and that's what we're doing. All right, now the next one is another inductive reasoning question. What is the sum of the first consecutive odd numbers? All right, first of all, let's kind of come up with some terminology here. Consecutive means in order. So consecutive is one right behind the other. Odd numbers are 1, 3, 5, 7, 9. So they're looking at the first 14 consecutive. So 1, 3, 5, 7, 9, 11, all the way until you get 14 of them. So let's kind of take a look at that. We're looking at the sum of the first 14. So the first one would be 1. The second would be 1 plus 3 is 4. And again, I'm looking for a pattern here. Then 1 plus 3 plus 5 is 9. 1 plus 3 plus 5 plus 7 is 16. So this is the first, let's see, 1, 2, 3, 4, 5 numbers. All right. So I'm looking at the sum. So 1, 4, 9, 16, 25. Now, there is something special about these numbers, and unless you have done math a lot, you may not pick up on that, but it turns out that these numbers are perfect squares. So like 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, 25 is 5 squared, and so on. Now you have a choice whenever you're working this out. So in this problem, you could, because 14 is not a lot, you could just list the first 14 numbers and take out a calculator and add them up. But what if it had asked you for the first 150 consecutive odd numbers? I mean, who wants to add up that? I mean, that's a lot. Or what if it had said the first 1,000 odd numbers? Nobody wants to sit there and do that. And so if we could come up with a pattern, that would be a whole lot easier. So the pattern here would be to come up with a formula. So the formula is actually that it's the number squared. So in other words, the first 14 consecutive odd numbers should be 14 squared. So if I'm looking for 14 consecutive, then I'm going to say 14 squared, which is 14 times 14, which turns out to be 196. So the answer to this question is 196. So that should help you with this problem whenever you get to it in the homework. But it's coming up with, so inductive reasoning is kind of looking for patterns with small situations and applying them to large situations. All right, so hopefully that helps you with inductive reasoning. Now we're going to look at deductive reasoning. So deductive reasoning is problem solving based on a formal structure of logic. And you've probably kind of seen puzzles that use deductive reasoning, and we're going to actually do one of these puzzles to kind of help you figure that out. So problem solving based on a formal structure of logic. So let's take a look at one of these. So here's an example. Abigail, Oliver, Rosa, and Blake all attend the same summer camp where they kayak, rock climb, and I forgot in here. It should say cook, kayak, rock climb, and zip line. Sorry about that. Each child has a different favorite activity. Can you figure out who likes which activity based on the following clues? Okay, so we've got 4 clues. Abigail's favorite activity isn't rock climbing. Oliver is afraid of heights. Rosa can't do her favorite activity without a harness. Blake likes to keep his feet on the ground at all times. And I've given you a chart here to kind of help you. So let's take a look. We're going to take each one of these clues and kind of try to eliminate some of the different options. So the first one is Abigail's favorite activity isn't rock climbing. Okay, so what I'm going to do is I'm going to go to my chart and I'm going to put an X1. That tells me the first clue eliminated rock climbing for Abigail. All right, and that's pretty much the only thing that it eliminates for me. All right, number 2, Oliver is afraid of heights. So if Oliver is afraid of heights, then that should eliminate rock climbing and zip lining. All right. He should be okay with cooking and kayaking because, yeah, that should be okay with him. All right. Rosa can't do her favorite activity without a harness. Okay, a harness. So she must like rock climbing and zip lining because those are the harness things. So that means we're going to eliminate cooking and kayaking with her. Okay, so that's what we're going to eliminate with her. She can't do her favorite activity without a harness. Does that make sense? I think so, yeah. All right, now Blake, here's number 4. Blake likes to keep his feet on the ground at all times. All right, so let's think what that means. If he likes to keep his feet on the ground at all times, then that means he definitely cannot kayak because, well, you don't have your feet on the ground all the times. He cannot rock climb, nor can he zip line. So it turns out that we were able to determine Blake is the cook. So Blake did the cooking. Okay, so that's great. But now, if Blake is the cook, that means nobody else can be the cook. So actually, that clue helped us we can eliminate Oliver cannot be the cook, nor can Abigail. Okay, so that's good. Now, when we did that, take a look at Oliver. So Oliver, the only option left for him would be kayaking. So that's great for him. So if he is the kayaker, then nobody else can be the kayaker, which means Abigail cannot kayak. So number 4 knocked her out for that one. Well, that means that Abigail has to be the zip liner. Oh, well, yeah, and Rosa has to be the rock climber. And so that one last thing for Blake, like, sealed the rest of everything else. Okay. So that wasn't that bad at all. So that is deductive reasoning. So deductive reasoning is not necessarily looking for patterns, but rather looking at logic statements and combining those logical statements. Okay, we're going to look at a little bit more about deductive reasoning. And you have a couple of problems where you're asked to use these Euler circles to check validity of arguments. Okay, so let me show you how Euler circles work. So these Euler circles, this is called a syllogism, and I'll show you kind of how it works. All teachers are crazy. Miss Baker is a teacher. Therefore, Miss Baker is crazy. So let's check to see if this is a valid statement or not. So we're going to take the first circle that we're going to do is our teacher's circle. All right, so here is our circle with all of our teachers. All of our teachers fit in this circle, and according to this, all teachers are crazy. So all teachers are inside of this circle, and therefore they're crazy. Okay, now it says Miss Baker is a teacher. So if Miss Baker is a teacher, then does Miss Baker live inside of the circle or outside of the circle? If she's a teacher, then Miss Baker has to live inside of the circle. So I'm going to put a little circle inside of here, and there's where Miss Baker lives. So my question now is Miss Baker crazy? Well, if all teachers are crazy and Miss Baker lives in this circle, then yes, Miss Baker is crazy. That's a valid statement because Miss Baker lives inside of that crazy circle. So that's how a Euler circle works. All right, that is a form of deductive reasoning. Okay, let's look at one more of those. All right, no children eat collard greens. Robert eats collard greens. Robert is not a child. Okay, so a little bit different. So first of all, let's form our circle with children. Okay, our children, this is our circle with all our children in it. Now, notice here that our statement says no children eat collard greens. All right, then it says Robert eats collard greens. All right, so if no children eat collard greens and all my children are inside the circle, then if you eat collard greens, you have to live outside the circle. So where does Robert live? Robert lives outside the circle because he eats collard greens, right? So here's Robert. He lives outside the circle. So then it says Robert is not a child. So is that a valid statement? Robert is not a child. That is a valid statement. According to those circles, that is true. Robert is not a child. Okay, so I know those seem silly, but that's just a different way to use deductive reasoning to form the validity of different arguments. Okay, that is the end of section 1.2. I hope that you understood all of those. If you need to go back and replay any of those, feel free to do so. If you have any questions, let me know.